So welcome back for lecture 3. In this last lecture, we're going to be talking about the abelian Higgs model. So before we get into the geometry, let's recall the basics of complex line bundles and Hermitian line bundles. And if this is all familiar to you, feel free to skip ahead, 5 minutes or so. Okay. So recall that if we're on a closed oriented Riemannian n manifold, a complex line bundle, L over M, is a 2 plus n dimensional real manifold with a surjective map from L down to M, such that each fiber, so the preimage of P under pi, L sub P, has the structure of a one-dimensional complex vector space. Okay, so we just have a family of complex vector spaces sitting over our base manifold M. So equivalently, we can say we have a real vector bundle of rank 2, so a family of two-dimensional real vector spaces sitting over M, equipped with some linear map J from LP to LP, which squares to minus the identity, right? And this is just our multiplication by I. So the simplest example, and in fact the most important one for most of what I want to talk about today, is just a trivial bundle. So we can take L to just be the product of C with M, right, where pi of Vx is just X and M, and the fiber over P is just C cross P, and we just give C the usual complex vector space structure, right? So it's just the obvious example, and in fact, for everything we're talking about in this lecture, it's perfectly fine to just think about this one, right? But just to have an extra one in there. Of course, there are many important non-trivial examples of complex line bundles. So an important early one would be the tangent bundle of a Riemann surface, okay, where it inherits the complex structure from the complex structure on the Riemann surface. Okay, so this is all familiar stuff. All right, by a section of the bundle, written U as in gamma of L, we mean a map U from M to L, such that U of P lies in the fiber over P for every P and M. Right, so on the trivial bundle, a section is just given by some map of the form U of X is V of X comma X for just some complex valued map V from M to C. On the tangent bundle of a Riemann surface, a section is just a tangent vector field. This says complex vector field, please ignore that. I just mean a tangent vector field in the usual sense on our surface. So exercise, a complex line bundle is trivial, i.e. isomorphic to the trivial bundle C cross M, if and only if L admits a section U and gamma of L, which is nowhere vanishing. The idea being, right, that this is going to give us a smoothly varying basis for our vector space over the entire manifold M, for our complex vector space. A fact is that for a generic section, U and gamma of L, the zero locus, Z of U, so all the points in M at which U vanishes, is an embedded oriented n-2 submanifold of M. And a deep fact is that the homology class of that submanifold Z of U in Hn-2 depends only on the line bundle L. Okay, so you choose a generic section, you look at the points where it vanishes, and look at the homology class of that n-2 submanifold. That homology class is only depending on L. So together with Poincare duality, this assigns to L a cohomology class in H_2 with integer coefficients, which is called the first Turing class or the Euler class of L. And in fact, it determines L up to isomorphism. Moreover, it's a deep fact in algebraic topology that every rank 2 cohomology class can be realized in this way. Okay. So a Hermitian line bundle is a complex line bundle equipped with a Euclidean structure, which is just an inner product in every fiber, such that the complex valued map is an isometry. Okay, so we have an inner product on each of these complex vector spaces in our bundle, such that multiplication by I is just a rotation. Okay. So for instance, on the trivial bundle C cross M, we can just take this to be the usual inner product on each C. Okay. A connection nabla on L is a first order differential operator on sections, which gives a notion of directional derivative of U. So to each U, it takes nabla U, which is going to look like it's going to live inside the space of one forms tensored with L. It's going to assign to each tangent vector, X in tangent to M, vector nabla sub X of U and LP in such a way that the following are satisfied. Right, so the assignment X goes to nabla XU is going to be linear in that tangent vector X, So it's going to particularly define some kind of one form pointwise, right? And moreover, it satisfies the following kind of linearity in sections. So nabla x of u plus v is nabla x u plus nabla x v, and nabla x of f times u, where f is some scalar function, is going to be f times nabla x u plus the derivative of f in the x direction times u. Okay, it's just the usual sort of Leibniz type rule we expect for connections. Most of you have probably seen connections before, so feel free to skip past all of this. Okay, finally, we say that this connection is Hermitian or Euclidean if it respects this inner product. And what I mean by respecting this inner product is that if we differentiate the inner product of two sections u and v in the direction of some vector x, then that's the same as taking nabla xu paired with v plus u paired with nabla xv. So we satisfy this kind of Leibniz rule with respect to the inner product. Okay, so that's a Hermitian connection. So an exercise for two Hermitian connections, nabla and nabla prime, on a Hermitian line bundle, there exists a one-form alpha such that nabla prime differs from nabla by minus I times alpha. So that is nabla prime xu is nabla xu minus I times alpha of x, so this one form eating that vector, times u for all sections u. So in particular, the space of Hermitian connections, it looks just like a single Hermitian connection and then varying by some one form, okay? And if we're looking at the trivial bundle, then all Hermitian connections just have the form d minus I alpha, where alpha is a one form. And by d, I just mean the kind of obvious connection given by sending v of xx, where v is some complex valued map, to dv of xx, where we're just differentiating that complex valued map. Okay. So note that if we have an S1 valued map from M to S1, then this is going to define an isometry on each fiber of our bundle, right? So at each fiber P, we have this map phi of P, which is going to rotate the vectors in that fiber LP. And we're going to call such a map a Gage transformation. Okay, so it's a map from M to the symmetry group of our fibers. Okay, and we're going to call the space of maps from M to S1 the Gage group G. Okay. So exercise, given a Hermitian connection nabla on L, and given a Gage transformation, so some map from M to S1, define a new connection nabla upper phi to be nabla minus I times phi star of d theta, so the gradient one form of this S1 valued map. Okay, and then you can check that nabla phi acting on phi u is exactly phi times nabla u for any section u in gamma. Okay, so if we had a section u, which our original connection nabla saw as constant, for instance, well then nabla phi would use the rotated section phi times u as being constant. Okay, this is what we call the action of the Gage group on the connections, or on the Hermitian connections. Okay. So the curvature, f sub nabla, of a Hermitian connection nabla, is just the commutator of nabla with itself. So namely, given tangent vector fields x and y on M, and some section u and gamma of L, we define f nabla xy acting on u to be the commutator of nabla x and nabla y acting on u. We have to add this in this little nabla of the commutator of x and y. All right, so presumably you've all seen this definition of curvature before, at least in the context of the Levi-Civita connection. Okay, so on the trivial bundle, note that writing nabla is d minus I alpha for some one form alpha. A direct computation, which I'll leave to you as an exercise, shows that f nabla of xy acting on u is exactly minus d alpha of xy. So just the exterior derivative of that one form alpha. So we get minus d alpha of xy times I times u. Okay. More generally, if we have some non-trivial Hermitian line bundle, then f nabla can be written as f nabla is minus omega nabla times j, or multiplication by I, for some closed two form omega sub nabla, whose de Rham cohomology class in H2 coincides with the Cherin class. Remember this this integral degree 2 cohomology class we saw earlier, modulo torsion. Okay, so it's the image of the first Cherin class when we tensor with R and forget about torsion. Okay. So simple exercise is to check that this curvature f nabla and corresponding with this two form omega sub nabla are invariant under Gage transformations. So in the sense that f nabla upper phi is equal to F nabla for any change of gauge phi. Okay, so these are just basic structural things about these bundles. So now we can introduce our functionals. So given a Hermitian line bundle over some manifold M, given a section of that bundle and a Hermitian connection nabla, we can consider the self-dual U of 1 Yang-Mills Higgs energy for some parameter epsilon. It's going to be the following. So we have the Dirichlet energy of that section measured with respect to our variable chosen connection nabla, plus epsilon squared times the curvature squared of that connection, plus this potential, which looks just like what we had before, 1 over 4 epsilon squared times 1 minus norm u squared squared. Okay, and this is equivalent up to rescaling to the epsilon equals 1 energy, where we're just taking nabla u squared plus curvature squared plus this potential squared found in the epsilons. Okay. So to get a feel for what this energy is doing, let's consider first what the zero energy solutions look like. So first note that E epsilon of U nabla is 0 if and only if, well, first of all, L is trivial, and the following hold. U has norm 1 everywhere, right, since this potential has to vanish. So we're looking at a unit section. Nabla U is 0. So U looks constant with respect to our chosen connection nabla, and the curvature vanishes identically. And in fact, it's an easy exercise to check the two conditions are enough to imply the third. Okay. So for the complex Ginzburg-Landau functionals of the previous lecture, the only zero energy maps were the constant maps to the unit circle. So in contrast now, the space of pairs U, nabla on the trivial bundle, for which E epsilon of U nabla is 0, is much larger. So why is that? Well, first note that if we take a constant map to S1 on the trivial bundle, and take nabla to just be our trivial connection D, well, then certainly that's going to be a pair satisfying these conditions above, a unit section and a connection which sees it as constant. And so that'll give us one pair with zero energy. But these energies are also, it's easy to check, gauge invariant. So if we take E epsilon of phi U times nabla phi, so if we act on this pair U nabla by a change of gauge, then we get the same energy back for any gauge map phi from M to S1. So as a consequence, if we take U to be phi of x comma x for any S1 valued map phi, and we take nabla to be the gauge transform of the trivial connection by phi, right? So we get D minus I phi star d theta, then we get a new zero energy pair for every S1 valued map. So in particular, all S1 valued maps are seen as trivial by this energy if we choose our connection correctly. And that's going to be a key qualitative distinction with the functionals of the previous lecture, where we were looking at something that was telling us about the Dirichlet energy of S1 valued maps. Now somehow all S1 valued maps look the same up to changes of connection. Okay, so that's a key feature given to us by the gauge invariance and our ability to choose the connection. Okay. So denoting by omega nabla this real valued 2 form, such that F is minus I omega nabla, it's easy to check that this pair U nabla is a critical point of E epsilon, if and only if it satisfies the Euler-Lagrange equations. Nabla star nabla U is 1 over 2 epsilon squared, 1 minus norm U squared U, and epsilon squared times the D star of omega is exactly the pair of nabla U with IU. This is this one form. Okay. And an important claim, which turns out to be not too hard once you know where to look, is that for any pair, say of regularity W12, solving these weakly, there exists some gauge transformation, so some gauge equivalent pair V nabla prime, just given by rotating U and acting by the same change of gauge of the connection, such that V nabla prime is a smooth solution. All right, so the gauge invariance kind of gives and takes away. Given any weak solution to this guy, we can always gauge transform it to get a smooth one. So we have a good regularity theory modulo change of gauge. Okay. Okay. So now let's get a bit into the geometry of these functionals. Okay. So for bundles over a Riemann surface, it was observed by Bogomolny in the 70s or 80s that minimizers of these functionals satisfy a special first-order system called the vortex equations. So we saw a general critical point satisfy the second-order equation, For minimizers in 2 dimensions, we have this first order reduction, where what does it tell us? So the section U is going to look roughly holomorphic or anti-holomorphic with respect to this connection nabla. And this curvature 2 form, which recall that we're on a surface now, so we can identify that 2 form with a function, is going to look just like plus or minus the square root of our potential term. Okay, and if you think back to lecture 1, this might call to mind this first order reduction for the Allen-Kahn equations that we had on the real line. Okay, and indeed, in his doctoral work, Taubes showed that all finite energy critical points of these energies for the trivial bundle over R2 satisfy these first order vortex equations, and moreover, they're determined up to gauge equivalence by their zero set. Okay. Moreover, he showed that any collection Z1 through Zn of possible zeros counted with multiplicity of this section U, any can arise as zeros of a critical point U nabla, and the energy E of U nabla of those critical points is going to be exactly 2 pi times n. So unlike these Ginzburg-Landau energies where we were seeing, degrees squared and interactions between points, for any collection of points in the plane, counted with multiplicities, we can find a section and connection satisfying these first order vortex equations, which have that zero set counted with multiplicity. Their energy is exactly given by, up to a factor of 2 pi, the multiplicity of those zeros. And moreover, those solutions are unique up to change of gauge. So this is the kind of nice, strong connection between the codimension 2, or in this case, 0-dimensional area functional on the plane, right, for points in the plane, and these gauge theoretic functionals that's promising for the kind of connection we're hoping with in the spirit of the Allen-Kahn equations. All right, so in the 90s, still in 2-dimensional domains, Hong-Yost and Struve carried out the asymptotic analysis as epsilon goes to 0 for solutions of the vortex equations over closed Riemann surfaces. And what they showed is that as epsilon goes to 0, these curvature 2 forms converge distributionally to a finite sum of Dirac masses that represent the first Chern class of L. And they're going to be supported on the limit Z of the zero sets Z of U epsilon. Outside of Z, this U epsilon approaches a unit section, and nabla epsilon approaches a flat connection, such that nabla epsilon views U epsilon as being constant. So in particular, energy is all vanishing outside of these Dirac masses. Everything's becoming trivial outside of that zero set. All right, so in the first part of my work with Alessandro Pagatti, we carry out the asymptotic analysis for general critical points of E epsilon on Hermitian line bundles over an arbitrary base manifold. So we're looking at arbitrary critical points now in arbitrary dimension. And we show the following. So let U epsilon, nabla epsilon be a family of critical points for E epsilon on a Hermitian line bundle over a closed oriented Riemannian manifold. And suppose that they have uniform energy bounds as epsilon goes to 0. It's a natural assumption. Then the energy measures converge subsequently to a stationary integral n-2 varifold. We have that integrality now, supported on the Hausdorff limit of the zero sets of these sections. And moreover, to kind of mirror this Hong-Yost-Struve result from dimension 2, we observe that the n-2 currents dual to the curvature 2 forms converge to an integral n-2 cycle gamma, supported inside that varifold view. Okay, so now we're getting a nice stationary integral varifold from our energy concentration. No diffuse part. Everything is entering into this critical point of the n-2 area function. Okay, so the cartoon in this case, it's not very detailed, but it's the same kind of cartoon we have for the Allen-Kahn. Somehow, all of the energy is concentrating in epsilon neighborhoods of the zero set. Here we're looking at a 2-dimensional slice, right? And vanishing rapidly outside. And moreover, if we rescale an epsilon ball to unit size, we see something that's looking like a model solution in Rn as epsilon goes to 0. And for a somehow generic point along our zero set, it'll look like a 2D model solution like those ones characterized by Taubes. So it's a really kind of strong analogy with the cartoon we had for the Allen-Kahn equations. Okay, so the proof, needless to say, requires some analysis. But a key ingredient is the following relatively simple lemma, which should be compared to the Modica's gradient estimate from lecture 1. Remember, for solutions of the Allen-Kahn equation, we had this lovely estimate of Modica, which told us that the Dirichlet energy integrand was pointwise bounded above by the potential part of the integrand, right? So for these equations, right, these Gage theoretic equations, we show that for pairs which are critical over a base manifold, so we'll say with positive curvature operator, but you can remove the curvature condition and pick up some small errors, we have a pointwise inequality where epsilon squared times the curvature squared, so the Yang-Mills part of the energy integrand, is bounded above pointwise by the potential part of the integrand. So it's very much analogous to this Modica's gradient estimate, except where this Dirichlet term here is replaced by a Yang-Mills term. Okay. And the proof is, requires a little bit of work, but ultimately it's an exercise in the application of Bach-Nervitz and Bach-type identities and the maximum principle. Okay. So now if we're looking at geodesic balls of radius r, standard computations show that the critical points of E epsilon satisfy a monotonicity identity of the following form. So we see that DDR of E epsilon of a ball of radius r is bounded below by 1 over r times the integral over BR of n minus 2 times the Dirichlet part of the energy, n minus 4 times the Yang-Mills part of the energy, plus n times the potential part of the energy. So as an immediate application, we see that DDR of the energy of the ball of radius r is bounded below by n minus 4 over r times the energy of the ball of radius r. And for critical points of the typical Yang-Mills or Yang-Mills Higgs type functional, this is really the best you can say. So for a typical Yang-Mills type problem, you expect to see kind of a codimension 4 energy growth for your critical points. But by our pointwise estimate for F nabla for these equations, we see that this n minus 4 F nabla squared plus n times the potential term is bounded below, excuse me, that should be greater than or equal than, n minus 2 times the Yang-Mills term plus the potential term pointwise. Right, where all we've done is we've said, well, since this potential term dominates the Yang-Mills term, we can borrow 2 from that n here and get n minus 2 times this energy density. And putting it all together with that n minus 2 times the Dirichlet term here, we see that DDR of r to the 2 minus n of the energy on the ball of radius r is greater than or equal to 0. So in other words, the energy is growing at least like r to the n minus 2. So we're satisfying the same kind of monotonicity that we should get if we're approaching a minimal n minus 2 submanifold. Okay, and this is really a key technical ingredient. And again, the path we took to get there, really strong analogies with the path from Modica's gradient estimate to the n minus 1 monotonicity for the Allen-Kahn equations. Okay, so this n minus 2 monotonicity turns out to be really the main ingredient, together with some exponential decay of energy away from an O of epsilon neighborhood with a 0 set, and Taubes' classification of entire solutions in the plane, which altogether paved the way for this statement about convergence of the energy to a stationary integral n minus 2 varifold. So the statement about convergence of the curvature as currents follows from a comparison of the curvature forms omega nabla to these two forms, where the J of u nabla of xy is given by this kind of gauge invariant Jacobian plus some 1 minus norm u squared omega nabla acting on xy. Okay. And apologies, that should say Ju nabla of x comma y, not Ju nabla defined to be x comma y. Okay, little typo there. So in particular, it's easy to see just by Cauchy-Schwarz inequality that norm of J of u nabla is bounded pointwise by the energy density nabla u squared plus the Yang-Mills plus the potential terms, just our pointwise energy density. And moreover, that this J of u nabla form differs from the curvature form omega nabla by d of something which we can show vanishes weakly as epsilon goes to 0, right? Because this nabla uiu one form is bounded in L2 and concentrating on an n minus 2 dimensional set. So that's enough to conclude that it's vanishing in L1, say. So these currents are going to coincide in the limit. Okay. Of course, these results would only be interesting if we had lots of examples in hand. No such families exist, then we're proving the empty statement, right? So to this end, we show that on any Hermitian line bundle over any Riemannian manifold, there exists a non-trivial family of critical points satisfying the conditions of this theorem, such that they converge to a non-trivial stationary integral n minus 2 varifold. So in particular, if we apply this result to the trivial bundle, which exists over any base manifold M, we recover Almgren's existence result in codimension 2 by fairly clean PDE methods. For non-trivial bundles, we can find these solutions just by direct minimization. And it turns out they'll coincide with the minimal submanifolds we get by minimizing the n minus 2 varia. For the trivial bundle, we use a 2-parameter min-max procedure, similar to what Darwang and I looked at for the complex Ginzburg-Landau functionals. And we take advantage of the fact that these functionals E epsilon satisfy a nice Palais-Smale type condition after you account for the gauge invariance. So you have to do something called selecting a Coulomb gauge. It's a little technical work, but it's fairly straightforward once you look at it. Okay. And somehow what we're exploiting here is the fact that the moduli space of these pairs, where say U is non-zero and now some Hermitian connection, modulo the gauge group has a rich topology, which looks pretty close to the topology of the space of integral n minus 2 cycles. Okay. All right, more recently, Davide Parise, Alessandro Pigatti, and I have been filling in another piece of the dictionary between these U of 1 Higgs functionals and the mass functional on n minus 2 cycles by developing a gamma convergence theory in the spirit of the classical Modica-Mottola results for Alan Kahn. And so in forthcoming work, we show that for any family of pairs with a uniform energy bound, so not necessarily critical points, just some pairs, these sections are going to converge subsequently after a change of gauge to some singular unit section U, whose singularity is given by an integral n minus 2 cycle, which coincides with the limit of these gauge invariant Jacobians, which we defined before, right? Okay, so exercise, which I alluded to before, is that these Jacobians are pointwise bounded by the energy integrand defining our Yang-Mills-Higgs energies, right? So in particular, note that in contrast to the Ginzburg-Landau gamma convergence results, where we had to rely on these really delicate estimates of Girard and Sandier to show that our limiting current had mass bounded above, even though the Jacobians pointwise had no mass bound. Here, our sort of gauge invariant Jacobians have a really easy pointwise mass bound by the energy of these sections and connections. Again, very much in the spirit of the kind of bounds we see in the Modica-Mottola result, the Allen-Kahn gamma convergence. Okay, moreover, we show that any integral n minus 2 cycle can be obtained in this way from pairs such that the limiting energy coincides with 2 pi times its mass. And we use this to compare the varifolds arising from the min-max methods with the U of 1 Higgs functionals with those arising from Almgren's GMT methods. Okay? All right. So many open problems remain in the analysis of these PDEs and their relationship with minimal submanifolds of codimension 2. So an important direction is the study of stable solutions, and closely related to this, the study of families of solutions with bounded Morse index, which arise from min-max constructions. So in his lectures of this workshop, Darren Chung will discuss several results in this direction, aimed at understanding stable solutions of the complex Ginzburg-Landau equations and the U of 1 Higgs equations in certain model spaces. Okay, so that's an important direction to pursue to understand stable solutions in model spaces, to hope to build up our understanding of blow-ups of stable guys under the microscope. Okay. So another natural question is whether any compelling analog for this Allen-Kahn to minimal hypersurface correspondence, or the U of 1 Higgs to minimal n minus 2 submanifold correspondence can be found in higher codimension. So while there are several geometric PDEs which are known to exhibit energy concentration along minimal submanifolds of codimension 3 or 4 in certain contexts, okay, so we see some examples arising in special holonomy settings, for instance, the existence of a family of natural geometric PDEs whose solutions and variational theory correspond cleanly to those of the n minus 3 or n minus 4 mass functional seems a widely open question at the time of this recording. Of course, if you're watching this a year or 2 or 3 or 4 in the future, hopefully that's someone's found either a resolution or a good reason to think that such a thing doesn't exist. So it's kind of a deep open direction rather than a specific open problem. Okay. So that's all I wanted to say for now. I hope you enjoyed these lectures, and I look forward to talking to you at the question and answer session if you're watching this, shortly after it's come out. if you're watching this further down the road, you can feel free to shoot me a question by email if there's something you want to know more about. All right, take care.